Once attended a talk by Will Bright. He's a very famous game designer. He designed games like The Sims and SimCity and a bunch of those. And he gave a piece of advice which I liked a lot. He said he was basically tasked with a game developers conference. He was tasked with some topic or another about game design, high level and stuff. And he basically spoke about something totally different. And his piece of advice was that when in doubt, talk about your day-to-day problems. So now that Mike has solved the software problem, I'm going to talk about the hardware problem. So you have this. You have some piece of computer aided engineering software. Let's say you have a simulation solver, you have a geometry kernel, you have some constraint solver or whatnot. You run the software, it's ready. It scales linearly to 10,000 CPU cores. It's a really good piece of software. Your software engineers were like, wow, this is like just fantastic. And your target latency for individual operations is 200 milliseconds. This means basically that you get in a request from users, you need to fan out the request to all of these 10,000 cores, and then you need to get the result back in 200 milliseconds. It's quite a bit of time. I mean, 200 milliseconds in light nanoseconds, which is kind of the cycle time, it's like plenty. Like it's a crazy, it's eons of time, 200 milliseconds. But you know, in normal kind of computing, it's still like a pretty tight deadline. It's a doable but tight deadline. So now you're really, really excited. You're going to go, okay, fine. So what should I do? I should deploy it somewhere and have users use it, then off we go. So where do you actually deploy a piece of software like this? You're a software person, you want to figure out. The answer is Amazon. So if you guys just came here for the answer, it's done. It's Amazon. It's up on the whiteboard. Like you can all leave now. It's fine. Most of the time. We'll go into a bit why it's not always Amazon, but the first approximation is Amazon. That's the easy way to go. So we're going to talk about Amazon Web Services, what we call commodity cloud providers. So commodity cloud providers, there's tons of options here. Amazon is just one. There's SoftLayer, there's dedicated computers, and so forth. Then we're going to talk about workload-specific deployment environments. So that's environments that are designed for not just general-purpose workloads like web applications, but for example, are designed for high-performance computing. I'm going to take Google as an example here for a few reasons, but there's a bunch of players here. It's much earlier than with anything. The third option we're going to talk about is not cloud at all. That's a picture of a Blue Gene queue. Blue Gene is IBM's supercomputer. It's a really nice device. Gets you a lot of oomph. Lawrence Livermore Labs uses it. Costs like $500 million. And then as a bonus, we have a quick evaluation guide for how do you decide between these different options? How do you pick which option is good for you or not? So let's start with Amazon. The good thing with Amazon, which I can't overstress, is that it has a very, very strong ecosystem. So if you're doing anything where you want to use cloud, which is literally, I don't want to buy my own computers and rack them, which is a very, very good sentiment, mind you, Amazon is the place to go. They have something called the cluster compute instances, which are devices designed specifically for high-performance computing problems, which is actually everything computer engineering is high-performance computing by definition. The problems tend to be that type of thing. They have something called a placement group, which is limited to 20 instances. What happens, a placement group is literally a commodity 10 gigabit E switch, and the switch has 20 ports, so you can plug in 20 cables into it, so you get a placement group of 20 machines. You end up with 320 Xeon E5 CPUs, which is a pretty good number. It's not your 10,000, but you know, if you can hit your latency targets, whatever those be, with this device, go. It's really good. Like, it's perfect. Like, you have good support. Everybody knows this system. You can hire people all over the world to do it. So this is a good choice. There's one number, 0.625 gigabits per second per core. We're going to talk a bit more about it later, but that's a really important number, it turns out. Because what happens is that you don't hit your latency target. It's not fast enough. You think like, okay, fine, I'll read the manual. The manual says, well, you can just plug two placement groups together, and now you have double the devices. Sounds easy, right? No. It doesn't work. We'll talk about the symptom now. We'll talk about the cause later. What happens is you fire up the second placement group, and it's not any faster. And you take a look at your graphs, and it turns out your CPUs are spinning idle. See, here's a little dirty secret. There's lots of problems in the world that parallelize easily. Graphics is one of them, which is why we see all these GPUs running around and basically having huge scalability. You basically take small chunks of work, split it up across a lot of machines, and that's it. But those chunks of work don't need to talk to each other. If you have the fluid simulation, on the other hand, you have small pockets of fluid. Those pockets of fluid need to talk to the other pockets of fluid. There's a lot of communication going on. It turns out when you look at different options, you can't look at the CPUs. You need to look at the network. Because in almost all cases, unless you're purposely building hardware that has slow CPUs, and if you do this, you know what you're doing, you will see a case where network is always slower than CPU. In fact, almost all analysis of like parallel systems ignore the CPUs. They totally ignore it. They just look at network latencies. So it turns out when Amazon says you can get a placement group of 20, that's it. You can't get any bigger. So you say, okay, so Amazon is a general purpose provider. There must be options. There kind of is. The problem is almost none of those options are very productive. Like, they're not ready products yet. Basically what happens is there's a bunch of high-performance computing providers that are trying to make them into services, but it's very early days. The APIs are difficult. It's not easy to turn up capacity. It's kind of hard. Google, on the other hand, has started offering, as recently as 6 months ago, they've been taking, I think it's, they've been taking early beta customers. Now, they've been offering something that's slightly better. The good part with Google is that Google knows how to do APIs. It knows how to do services, but I'll preface this a bit here. I'll tread gingerly around Google, mainly for the reason I used to work there for 5 years. So I've actually like worked on the cluster management system. That's the team that builds it's basically the operating system for the whole Google fleet. It schedules all the programs. It makes sure everything runs on the different computers and so forth. The Google fleet, as you can imagine, is really big. So in some sense, there's some things I know which I can't tell you, and some of the stuff I know is undoubtedly. But what we know very little about the fabric, but as far as it looks like a fabric, the network fabric. It looks like something that's better than Amazon because it's purpose-built for Google. That said, they limit you currently to 8 instances. It's kind of like, you might solve your problem, they might not. You need to talk to them, you set up a meeting and so forth. This is clearly like, there's going to be a trend going on here. This is clearly not as cloudy as Amazon. Amazon was really easy. It's like you just like pull it up, pull your credit card, and you're going. Here you're not, like, you need to set up meetings and system and stuff to get this going. So it's not as easy as Amazon. It might work. There's one caveat. Google, when you go into specialized workload optimized computers, specialized means something. It means that if you specialize for one thing, you can't specialize in the second. Google is specialized for web applications. Very large-scale web applications, mind you, but still web applications. That means that for Google, it's okay for requests to take slightly longer if their utilization level is higher. So they're ready to trade off longer latency for better kind of throughput or utilization level. Most high-performance computing or engineering problems, again, are what's called latency. You have a problem, you want to find a result as soon as possible. It doesn't matter if you half your computers are sitting idle, if you can like squeeze that time down. So from a kind of engineering perspective or technical computing perspective, it doesn't matter. Utilization is not as important as latency. So there's a subtle kind of specialization there which didn't happen in that's kind of biasing it away from technical computing. This was a common discussion internally, is that why isn't Google doing like large-scale high-performance computing? And the answer is because the data centers are built around a specific type of load, and that type of load is basically web stuff. Right. So you're kind of like these specialty providers. 12 months from now, let's look at it again. It might be much better. Now it's not really getting anywhere. You can't buy this out of the gate today. It's not easy. So what do? You buy a BlueGenQ. Lawrence Livermore bought with BlueGenQ. It's a really good thing. The good part, it has a decent interconnect. It uses something called a 5-dimensional torus. A torus is basically a connection. It's a box, but where the edge nodes are connected like around the box to their neighbors on the other side. 5D means it's a 5-dimensional box. That means you have a lot of connections going on. It's actually a very good interconnect. In fact, the Blue Gene has been top on the top 500 supercomputer list for several years. I don't think it right now is. That's mainly because the measurement used on the top 500 list is linear pack, which doesn't actually stress network as much as it should. There's been a lot of discussion of the metric being bad. But Blue Gene is without doubt the best machine you can have. Like, if you want to have bang for buck, that's good. One critical number, which we looked at earlier, is that gigabit per second per CPU core. Blue Gene has 7 gigabits per second, which is over 10 times more than what you get at Amazon. Again, this number is really, really crucial. It turns out that a Blue Gene is able to achieve a 60% utilization level. 60. Like, this is a device that's purpose-built for running these problems and can actually get up to 60. They think 60 is like world-breaking good. I agree with them. It's still very far from 100. You're throwing away 40% of your CPU capacity just to run the stuff. The bad news is this is expensive. It's not as expensive as you think. You will be spending millions, but you're not going to be spending decamillions to get started. It's water-cooled, which means you're now running a utility, a small one. Depends on what you get excited about. Water-cooled is pretty cool, actually. It's really exciting tech-wise. But it means you have to have these people like going around and doing plumbing and stuff, which means that you're now running a facilities project because there's no data centers that are going to take this device in and run it for you. So you need to get somewhere to put it. You need to put electricity in. You need to put networking. You need to get the water in the first place, etc.
That's complicated.
This is not very cloudy. Well, it's not trendy in any way, but it's like you have capacity problems up and down. If you have too much capacity, there's no way you can sell it back. They come in like chunks. They come in rack-sized chunks, which use like, I think 30 kilowatts of power, which is a lot of power. It's probably this whole building complex uses that much. So you can't divide them in small chunks. Also, if you need more, you have to wait for a quarter of IBM to ship you more devices. So you're kind of in a bind if your utilization plan didn't work out what you thought it was. That's very hard to fix. So here's a quick evaluation thing. If you get this far, it means you're really interested in the problem. The first observation is measuring working system is best. If you have an algorithm or software solution and a system, measure that works out. The second thing is dimensionality of your problem. This is a concept where if you think about the fluid simulation, again, it's the base dimension is 3, because it's a 3-dimensional problem. You have like 6 neighbors. This turns out not to be true. In most cases, the dimensionality of your problem is more than 3, because you have adaptive meshes, you have dynamic meshes and stuff. All these conspire to make your problem higher dimensional than 3. Basically, dimensionality is important because topology is important. When you look at these internet diagrams, you have the cloud in the middle, and the computers are happily connected to it in the star. It turns out this only works for small switches. When you go further out, topology, like how the wires are connecting the different nodes in the computing set, and the intermediate switching nodes that are pushing packets around, it's actually very important. I mean, it might be physical cables, it might be traces on a PCB, it might be down in the silicon substrate, but there are wires. There's some kind of connectors, some lanes that send signals from one point to the other, and how you wire those lanes up is important. Stuff about topology is important. Hop distance. So if you have a problem of, say, 6 dimensions, how many hops do you have to go out before you find the neighbors you need to talk to? In a good system, in a good topology, that's 1. All your neighbors are in your 6 dimensions around you. In a bad system, you might have to go several hops out to find them. Another number is bisection bandwidth. Bisection bandwidth is basically you take all the nodes in the system, you find a cut where you cut the system in half. and you pick the cut that has the least links, wires going over, and that's your bisection bandwidth. There's a theoretical proof from 97 basically saying that for higher dimensional problems, you will always be bounded by bisection bandwidth. So bisection bandwidth is actually the number you need to be looking at. So hop distance, bisection bandwidth. Hop distance is more for lower dimension problems. Bisection bandwidth is stuff like sorting. So I'll pick two topologies. There is actually a bunch. So the first one is a fat tree. A fat tree, what you see in most data centers. You have rack level switches, you have like higher level switches, like these big Cisco Juniper switches that put everything together, and then you have connections out. A fat tree is relatively easy to wire, but it's very expensive. The Juniper switches, those with like 100 ports, 200 ports, could easily cost you several million. And it's also a very, very, very bad topology. It performs really bad. Your hop distance, in many cases, is 2 to the power of levels. You're going to be talking across the network to your neighbors all the time, and the bisection bandwidth is really poor. So a typical example is from 1 gigabit E machines. There's still a bunch of them on top 500, is that they literally get those 15% utilization levels. Most of the cluster is idle, waiting for like some core switch that's like totally overloaded and can't do stuff. The torus topology is another topology which is really common, mostly in like supercomputer environments. It's a good topology if the dimensionality of your problem is less than the dimensionality of the torus. Then you're okay. The problem is it's really expensive to wire. There's a lot of manual labor in actually wiring it together. There's a reason why the IBM technicians come on site and spend like 2 months wiring up the glue and queue, because they're trying to get all those connections up. There's no regularity to these like higher dimensional topologies. There's no way of you taking like 10 cables from one place and plugging them all in. You need to actually like take one cable at a time from each place. There's like a big map, and you're trying to get all those cables correct. If you screw it up, you need to kind of find a bug and fix it. So that's not a really good, it's not easy to wire those up. Once you kind of understand the topology, you also need to look at the actual tech. You need to look if it's copper, you need to look if it's fiber, you need to look at, well, copper and fiber are big choices here. Copper is obviously better. You go from an electrical domain. You keep inside the electrical domain when you go from CPU to CPU. If you go fiber, you need to go out to the optical domain in between. Then again, copper does not scale very well with high speeds and long distances. So a copper cable that can, like for InfiniBand coupled cable, that can do like a few, like let's say 10 feet, is really expensive because there's going to be like coaxial cable around it, like shielding and stuff like that. Fiber is much more expensive or much easier and longer distances. So this is what you need to know. It sounds like a lot, doesn't it? It's actually the start. Like I asked my systems engineer for a paper reference thing, and he sent me like these 40 papers to start with. So, but this is a good list. This is going to get you started. Like if you understand what's going on here, you can be able to evaluate the different options as you go. This is going to help you evaluate the Amazon option as well. It's a start topology. If you add more locality or the groups, you're going to get a fat tree. Ergo, it's not going to work too well. So back to the beginning. So these are really your options. A, you pick Amazon. If it works for you, great, fantastic, really good, congratulations. Anything else? Prepare to spend a lot of hours just researching the topic. You're basically running into the hardest computational hardware problem there is. There's a reason why IBM has spent 10 years trying to solve this problem, and literally like pretty much everyone else. When you run in, this problem is the same problem that stops nuclear explosions from being simulated more efficiently. For some reason, there's a lot of military interest in getting that done. So there's no easy solutions. There's no kind of prepackaged solutions in this space, but there is a lot of knowledge on how to approach it. Again, in most cases, you can do Amazon. It usually saves you. There's a lot of good things there.
Yes.
Otherwise, well, good luck. You're going to need it. Questions? Shoot.
An InfiniBand solution versus a 10 gigabit Ethernet.
So the question was, what improvement are you going to get from InfiniBand versus 10 gigabit Ethernet? So there's two things. First, InfiniBand is optimized for low latency. So that means that both the network interface cards the switches and everything in between is optimized for. In many cases, it does cut-through networking, which means like that basically all the hops between the two kind of user spaces. So user space memory is one end, user space memory on the other end. All the hops are optimized for the packets going through really quickly. 10 gig Ethernet, that's not true. So 10 gig Ethernet switches are notoriously slow, especially if you go to those multi-port switches up in the factory, like in data center. They're really slow. You might see some kind, well, not millisecond, but in some cases, millisecond latencies for a packet coming in on one port and actually going out on the second port. The second thing you gain is that you gain speed. So 10 gig Ethernet is 10 gig. Infinite band has QDR, which is 40 gigs of like capacity per link. The third thing you gain is cost. It's a lot more expensive too. We look at top 500. There's really two types of topologies around, or two types of network fabrics around. There's custom fabrics like IBM's 5D Taurus, and Cray still has. I keep forgetting the name. They have a custom 3D, 4D solution, and then there's InfiniBand. So it's certainly a good choice. But very few providers, you can't get it from any kind of commercial provider right now, like a cloud-based solution, sadly. If that answers the question. Okay, good. More questions? Okay, perfect. Thank you.
All right, thanks.